Okay, so I'm going to get started today. I'm going to start just by introducing a bit about the course and kind of how we're going to run it. First off, let me introduce Alan at the back, who is joining us as our TA. He's from the Tabasoy lab, has a ton of experience in R and Python, and in particular applying it to biological data, his own research. I'm Thomas Carroll. I'm the director of the Bioinformatics Resource Center here. So I don't do my own research. I support people like yourselves in your research. And one thing I do a lot is obviously bioinformatics, and particularly bioinformatics in R. And that's really what we're going to cover most of these sessions. In terms of attendance, so I think in the forms it says attendance mandatory, you have to be here every session. I understand that's not going to be possible. You will have lab meetings, you will have commitments in the lab. All I ask is if you're going to miss a session, please email me in advance, or at the very least on that day. This course is for credits, so I will go through and check that at some point just to make sure you're attending. If you're skipping multiple sessions, and that may be for a decent reason, your PI has changed your lab meetings to a Friday or something, please come and see me early. Maybe we can arrange something that I can support you outside of class. So as I said, hopefully you found this page. All our material is on this site here, Rockefeller University.github.io, and 99% of our material is here on the day we actually run it. We do run some paid courses and we delay it by a couple of months. And this is just so that we have a way of kind of supporting building new courses. But I think everything we've ever run, you'll find on this page. And I'm going to talk through kind of how that looks in a second. But really, this is like our homepage for everything we're going to run through. I'll point out very quickly, we have, thanks to Matt, who's in my team and does training wider for the university, we have a YouTube channel. And here's Matt.
Welcome to the YouTube channel.
So hopefully you can really kind of, if you do miss class, I'm recording this right now. Sometimes it will slow down my computer, so it may be problematic. But if you miss class, I'm going to try and make it available for you. So, you know, don't sacrifice your lab work. Just let me know when you can't be here. My fear is, and it's happened to me before, I have one person in the room and everyone else is, you know, watching on Zoom or something. Sucks for me. It's really great for that person because they get a one-to-one session. So just let me know, but, you know, I'm not expecting everyone to be here every session. So we have YouTube. All our material, as I say, is here. And we'll just look at what we're going to run through today. So we're going to run through a lot of this. Feel free to skip ahead. Feel free to look. I will say I will update a lot of these classes as I approach them with my team, and especially the single cell. So we have a boot camp now. We're going to try and turn that into what we will present here in the graduate school. There are no exercises, so I'm not going to give you coursework. But as we go through, we have extensive exercises. And I recommend you do these because very deliberately, the exercises teach you the additional bits you need to know. Okay, so if you go through the exercise, you will find things you need for later exercises. And I'm going to show you where they are in the class anyway. Okay, so this is our page. So as I say, this is all our material here. This is all kind of programmatically built. And we have please feel free to stop me if you have any questions. We have our web pages. All these should be tested on the time that I release these. So as I approach the class, bless you, we will compile these and make sure they're working for you. So right now, for our version 4.4, this all should be working on Mac, Linux, and Windows. Should. We'll see if that's true, but we test that programmatically. We give you a little overview of the class for every session, and we tell you some of the system requirements. So for the first one, you really don't need anything apart from R Studio and R itself, which I'm going to talk a little bit now. If you want to, I mean, so I've never taken any slides off this website. I promise it will be a permanent, always available to you outside of Rockefeller, in Cornell, or wherever we're from. But if you feel you want to, and you know, absolutely you can, just click here and you'll download the material. Okay, so that's going to download I'm not going to do it right now because I did it earlier. But that's going to download a folder for you, the name of the class. And in there, you'll have this R course. I think even this one, maybe, if I click this, that takes me to the old style. We've got a new style. If I go into R course, and I'll explain this in class again, click index, you have the same entire website that we have now on the web page. Okay? So everything you need, you can just download and keep it safe. But I promise you, we'll keep these web pages open and active indefinitely. The presentations themselves are embedded in these pages, so you can follow through like that if you want to. One thing I'll point out is we also have a single page version of everything, and that's because at some point you're going to want to start referring back to the first sessions, and those slides aren't searchable by doing Control F. So the single page, you can do Control F and search anywhere within the page. We also have all the code, so I think I extract every bit of code. So if you want to follow along, but you don't want to copy and paste from our actual slides, you can kind of click here. But it's also available up here in the exercises too, so you can get them from there. Last thing I'll point out, and I haven't really written this into our class, but we have a help here, right? So what I would ask you to do, if you have questions, ask me now. But if you're outside of class, we want to support you as well. You may not be here all the time. I ask you to basically sign up for GitHub. This is explained on our YouTube website. So Matt here will explain this, how you get help. But it should be straightforward. If you've got an academic email, it's free. You get a lot of benefits from GitHub. And effectively what we'll ask you to do is ask questions here. And the great thing about asking questions here is that you are not the only person really thinking about that question. Okay, so we have a lot of problems with this RIO package installation. And actually, this was kind of a TA in our first year, and he came on and helped people. And then other people can come look at those solutions. So it's really nice if you can put them there. And occasionally, I might rewrite the questions you're asking me and put them there. You just need to sign up to GitHub, and you can ask anything here. And the way to do it is just new issue. My issue is and whatever. And then you write a description here. And you submit that. And the real advantage of this is that you don't just get my attention, you get my whole team's attention. Right? So everyone from my team can hop on and try and answer this. And I encourage you to answer it for each other as well. You may have already solved this. It's really good if you can help each other out. I'm going to maybe close that issue so someone in my team doesn't question me why I'm editing a strange issue. Okay, so we leave all them open even if they're solved. I think Matt puts resolved them, but we don't close them. I think everything which has been closed. Oh, geez. Is that me saying that? Is there? Okay. Very offensive way to start our first session. Okay, so we really are, I understand we're going to move quick through a lot of this, but we can help you and support you outside. And hopefully you can review the material as we go along. I'll say that, a lot of the graduate school from previous years is already on YouTube. And Matt has also run kind of nice open sessions like what we're doing today. He's got an abridged version, reproducibility. So. Before we start, I'm going to say, so I'm not American, I'm British, Welsh. And I actually come from a little place called Mumbles, I kid you not. And I tend to mumble. If you can't follow along, please just let me know. I tend to start speaking quickly and to myself rather than to you. Just give me a hand and I will try and speak up a bit. So with that, we'll get started on the course. And I'm going to open up the slide here. Hopefully my computer can handle being on Zoom recording. Hopefully no one's in the room, but I'll put this up after the session. I would ask actually if we're, so last thing, this session is quite long. We have 4 hours, right? Which is a long time to keep on running. So what we're going to do is we'll do a 2-hour session. We'll have a little break. And then after that, we have the exercises. So if you need to head off and do those exercises in your own time, I'm absolutely happy with that. But I will be in the room, Alan will be around, and we're here to support you to make sure that you can follow along. So don't just rush off if you have questions. We're here, but we're going to put that together because what I found is if I had an hour gap, people would finish the exercises in 5 minutes and then kind of go away and maybe not come back. So, let me know if that's not working for you, and maybe we can think about something different. So, as I just said, the overview of what we're going through today, we have a course homepage, and feel free to step out, have a break if you need or whatever. We have a course homepage I've just shown you. I'll show you a bit about setup, but we may need to leave that until the break. If you need me to come onto your computer and help set up R and RStudio. Okay, so right now, today, it's going to be very simple, background to R, some simple things. But we're going to talk a little bit about R and RStudio, now posits kind of setup. I'm going to talk a bit about the background for a few slides, and then we're going to talk about the different types of data in R, how you handle strings of numbers, strings of letters, words, more importantly, tables, how you get them in and out of R as well. And I think in the second session for this first part, we'll actually start to do some conditionals, looping, if, or, etc. And again, feel free to stop me, interrupt me. So all the prerequisites that I showed you, they're always available on GitHub. We will never take these down. Luckily, we're very supported by Rockefeller to keep this training up. So should always be there, but you can download it here. Like I said, once you've downloaded it, maybe I didn't say because I just pointed you to the index file. But we have this index file, but then you'll have presentations, and that's also contains all these slides, etc. The index file will link you to them. We have data for the exercises. We actually have the exercises. I give you the answers as well because it's important that you have them notes with you. I would advise having a crack at the exercises. Don't just jump to the answers, but never walk away without seeing the answers, and then various scripts, etc. That's the material, but again, you can just follow the website or you can follow that index and it'll take you to everything. So one really important thing, and I'm going to show RStudio in a second, so I'll probably wait to that, is to setting your working directory. So any programming language, it has some idea of what file, what folder it's in right now. So if you want to read, say, an Excel or a CSV, a text file, you need to know where your program thinks it is. Is it in this folder? If it finds that text file in the same folder, it's easy to read. But we can also set full paths or paths to these on your computer. Choosing your working directory just says, this is my kind of where I am starting when I'm looking for folders and files. So when I do this, I set up my working directory to be in the R course. I haven't actually shown you RStudio yet, but I'm going to show you that now. I'll show you that in a few slides. So does anyone here have any experience with R? Anyone have any experience with other programming languages? Any other one having experiences with programming languages other than Python? Great. Can anyone do C++, C, Rust? What was the other programming language? Oh, Bash scripting. That's very useful as well. Any other languages here? Java. Who said Java? Oh, great. Anything else? MATLAB. Do you know MATLAB is fantastic as well? So, R isn't like Python quite that. It's more of a statistical kind of computing language. It's a scripting language. But it is, what they would say Turing complete. You can do anything you can do in any other language you can do in R. But when I say a scripting language, it's really meant for high-level data analysis. You probably shouldn't be, if you've got a 50 gigabyte file, you shouldn't be working or writing parsers for that file necessarily in R. And I'm going to explain a bit more of that. So R was developed by Robert Gentleman and Ross Ihaka. So the R's from them became the R in R. And both of them, I think, worked at Bell Labs, where we have S, which I think still exists. And S was proprietary. It was owned by Bell Labs. It was a scripting statistical language. So these guys decided they're going to make an open source version. So it's freely available. You don't have to pay a subscription for it. And they made it cross-platform. They say high-level data analysis. Really, it's for working with smaller data sets, I would say. I mean, now we can scale up, and smaller, I mean anything up to multiple gigabyte files. if you wanted to parse, say, all of Walmart's purchasing data in the last year, you probably wouldn't be doing that in R, you'd be doing that in C or Python. One thing which I think is unparalleled with R is its graphics capabilities. You can do some fantastic plotting in R, and we'll show a little bit of things like ggplot later, but also extending that into interactive plotting. R really, I think, has some great capabilities there, and we'll show a lot of that. It has a really nice range of add-on packages, and in particular, this is why I got into R, because I used to do Java. That was my programming language. So if I wasn't thinking this, I really like Java. It's just not written for biological data so much, right? So we'll come on to our second sessions as things like Bioconductor. And these are wonderful packages written for processing very common biological data types. And that's why we can still do this high-level data analysis, because we have functions and tools to interact with very particular biological data types. What makes R, as you start to work through it and when you start to use it, what makes it really great for doing your own analysis is this active community of developers and thorough documentation. A lot of programs, and I'm going to say maybe Python a bit as well, because we do a lot of Python too. The documentation isn't so good. And that's because R has built into the way you create packages tests for the documentation. So you have to kind of have good documentation. Otherwise, you won't be in things like CRAN or these major repositories, Bioconductor. So it's forced on them. And that's fantastic for us. And this community developers, people are really friendly to a point. Is that true? If you ask in the right places, people are friendly. They have rules about how you should ask questions, and we'll talk a bit about that at the end. But there are people, and it tends to be postdocs, PhD students writing these packages, and they want to interact with you. They want you to work and use their package. So they've got an active community developers. We're not going to talk about developing our packages here, but if you're interested, let me know. There's Matt and my team, who I just showed. He's very keen to do a training course on that. So we can add trainings with it. Again, I'll say, if you have suggestions for this course as we go along, I've already had some. We haven't even started the class. People are asking me to add things. Let me know, and I can think about trying to add a session or add something on this. So I say R comes with excellent out-of-the-box system and plotting capabilities. Provides access to thousands of packages. Actually, MRAN's dead. No, I'm afraid that was done by Microsoft. But CRAN RForge is now something called RHub. Open that tab, maybe. So this is CRAN. This is actually where you download R from. It's the comprehensive R archive network. No one said Perl when I said programming languages. Okay. But actually, this is all based on the way Perl set it up, which was originally CPAN. So they've taken it from Perl. It's something which Perl gave us, but something else I learned, which I've never used since. And on here, packages, open this, and it's going to be, it is an extensive set of packages, actually. It's going to take a while to load, I think. It's a never-ending set of packages. It's so well supported. Okay. Robert Gentleman. Have we just lost the internet in this room? No. Robert Gentleman, so one of the R's, he started this Bioconductor project, and really it was written around microarrays back in the day. So, stuff I was doing. But this is extended now, and I say hundreds of packages, thousands of packages. Bioconductor's kind of gone exponential in what people are contributing. And now single cell, proteomics, image analysis. A lot of you'll find a lot of that in R. Actually, MATLAB is particularly great for image analysis as well. So R is freely available. As I say, it's open source. We can download it. You should be able to go to this CRAN website, and there should be a link on our front page there. If I was just on CRAN, I'll go back. And go back one more. You can just click your particular installation. You can just follow through and install it. I will be around at the end. If anyone hasn't got R, I can help you install this and get it set up. And another thing we're going to use is something product called RStudio They've actually changed their name to Posit now, and that's because they want to cover Python as well. But RStudio, I say it should already be on your machines. Probably not, maybe for everyone. But you can click here and it should take us to RStudio site. Posit now, sorry. And on here, there it is, download RStudio. This is their prime product. Okay, so whereas R is the actual language, it's what we're actually going to program in. RStudio is what we call an IDE. It's an integrated development environment. And it's just like a friendly way of interacting with R. And it's certainly the one we've chosen to use. So let's just have a little look at R. I think I've got like a slide on this here, but I can just show you what RStudio looks like. Okay, so this is again our link to our website here. But what we have is the actual the RStudio window is here on the bottom left. I think I've been doing some programming here, so let me restart this. But if we look, we have on the bottom left the actual R terminal. So this is where we will type our commands. This is R itself. We have, I'm just thank you, sir. This is our kind of orientation window. It's going to tell us, so we're talking about working directories. I'm currently in this directory, showing me the files in that directory. So this means I can click them, open them, look at them, etc. Up here, we have what we call our scripting window. So if you actually want to write, and we're going to do this together, if you want to write your pieces of R code in here, 1+3, I can do that down here, and I can press enter, and it will evaluate once my R restarts. We can also put them up here and just select run. And it will be, or I can press control enter, command enter, and it's going to go and run that particular command. So you write your scripts up here, and you can kind of execute them down here. Up here in the top right, as everything's restarting on my computer, we have what is the environment window, I would say. So this is going to tell us what we have created in our objects, etc. Here actually gives us kind of a way to interact with it, and we'll look at that later on. Also, once you start getting to more complex stuff like building packages and GitHub, this will all pop up here as well. I think this isn't going to, history. You also have a history here. So everything I've typed in. So I've got lots of commands that got my environment back. Here we go. So I've got a table here, and I can click that and look at this in some way. We're going to talk about this later today or maybe next time. Is anyone in the Darnell lab here? Oh, yeah. So you recognize that data. Nice thing about having history is occasionally you're going to wonder what you did. You can actually select it. If I want to reevaluate something, I can send that back to the source. And I can have it there, or maybe I want to send that to the console. So it's a nice little way of working with R. I'm going to clear this out now. But there are lots of choices. This is just our preference. Okay. My computer, I think, is a little slower because I'm trying to record it sometimes. So the first thing we're going to look at is different data types in R. And really, at the most basic, I should change this from a simple calculator. I'm not sure if people use calculators anymore. Maybe Excel or something. At its most basic, R can just do some very simple calculations. So we can do things like add two numbers, create a third number, times two numbers. Like calculators, we have access to functions out of the box. So on a calculator or in Excel, we can do average and give it some numbers. We have a lot of these built in for us right inside R. If we need more complex functions, we're going to see we can install packages later on. We don't have a clock. Like this. Okay, so I'm just going to open up R and just show you quickly. I'm going to actually avoid bouncing back and forward between R so much, but just to get us started. So 1+3, 4, 2 times 2, 4. Again, I can put these up here. If I do 2 times 2 up here, I can either run that line, or I think if I select that line and press Command Return on Mac, it will run that, and I can do multiple lines as well. Okay. I think we just saw there our first use of a function, so I did square root. And then I can do the square root of 4. And we'll give the answer back into the terminal. Okay. Okay. So just as, oh, yeah. So square root demonstrates the first use of a function. We're going to see a lot of functions as we go through. And the reason really is, as you may know, R isn't as fast as Java, it isn't as fast as C. But a lot of these functions are written in a different language. We interact with them with R, but it's going to send it to C, and it's going to execute them very fast. I mean, square root 25 isn't a problem. But for very complex things later on, you need to use functions really to do them for you. And I think that's a big difference between R and something like Python, especially Java. There often is a function written in one of these packages which will do the job for you, and that's written very efficiently. And it's better than writing it in raw R. We're going to see a lot of this. So the way, if we want to use functions, the way they work is you have the function name. So in this case, square root. I've got Slack open. Oops. We've got square root, and then we have these parentheses. And inside that, we put the arguments. So things we want to evaluate for that function. So in this case, I want to get the square root of 25, square root parentheses, and inside there, I put 25, and it returns, at the moment, the result to the screen. Okay. So that's a very simple function, the most simple I could find. We also have some other really common functions like min, sum, and max. In this case, if you want to get the min of these numbers, I just provide the arguments here separated by commas. Okay. So we have the function name in the parentheses, and inside there is the arguments we want to get the min of, and they're separated by commas. In R, all the arguments will always be separated by commas. Okay, so we've got the min, the sum, the max, very, very simple. R has many useful functions built in. So a lot of the mathematical functions, operations, matrix multiplication, this is all kind of built in here. There is a link to a list here, but I can tell you it's old and not super complete. We'll see later on that we can start to take advantage of all these libraries just by installing them from these repositories, and then we get access to all their functions once we've loaded them. But out of the box, we have a number of functions we can use. And I was talking about, documentation being great in R. For every function, a package can't exist unless there's a help page for it. It isn't possible. The package will not be in CRAN. It will not be in Bioinformatics. It's tested and checked. There are ways people can trick it, as we could, but let's pretend it's not. So if I do question mark square root, okay, it will open here. And if you're using base R, you're not using RStudio, it will just open underneath. Maybe I'll just quickly show that. So I do R here. So there, I'm opening a terminal here with R inside RStudio. Oh, how annoying. So if I do question mark square root, you can see it kind of prints the same help, but just in that session. Okay? This is a nice thing about RStudio is it kind of keeps it separate. And in here, we get some components. For every function has a certain set of components. We have a typo, a description. This can be good or bad. Well, let's check this. We have usage. So we know that it takes one argument, square root. This is on the same page as absolute, which is another function. They put it onto the same help page. We know that that argument needs to be a numerical complex vector. So numerical, these complex numbers. Gives you some details now on like how it's implemented, and it's probably gonna, if you go deep here, you'll see it's implemented in C. But most useful reference is square root in case you want to reference that in your paper. And then what's really useful is you have examples, right? So these are tested when the package is built. So we know these work. And if I take this now, and I copy this, and I put this into my actual console here, I can be guaranteed I will get a result for this. So I find these really useful. If I don't know how to function, it's really nice to have an example, right? And then I can kind of copy the example and adjust it. So that's a nice example, both of what a function is, but also with no robust documentation, hopefully, in R. So this is a very simple one. It just takes one argument. Okay, so we're not going to have very much complexity there working with square root. Arguments do have names and order. So with functions like I've deliberately shown now, min and square root, the arguments which can be provided are obvious. You get square root, I'm going to give it a number. I'm not going to give it a word or a string. For min, it's pretty obvious too. I'm looking for the minimum. I'm going to give it a set of numbers. Okay. Many functions, however, aren't so obvious. The arguments are a little bit more complex. And in that case, using this question mark to kind of look at what these take can be very important. So the one example I'm going to say is dir. So dir will list all the files in a particular directory. So you can imagine that will be very useful when you want to start reading files into R. You want to know what files are in that directory. Maybe you've created a directory and it's full of all your counts for every gene in the genome. You just want to list them and then loop through them and read them in. Okay, so dir can be very useful. But it has additional arguments, and I'm going to actually open up the web page here. Okay, we can see it's actually a little bit more complex. Okay. So I said arguments have names, and here we can see the first argument is called path. And arguments typically have defaults, right? So we don't actually provide necessarily any arguments to these, right? If we just take the defaults, here it's saying path equals, and it's telling our default is a dot, which means the present working directory. So it will list all the files in my present working directory. The second argument's my pattern. I can say put text there in quotes, and it will look for all text files. And we have various things up until a really useful one, which is full names. If I just list the if I ask it to list the files, it will just give me the name of the file. It won't give me the path. So sometimes I want to get the full path, and then I can use that to read it in. I need the full path. Okay, but we can see here it describes everything, but there is an order. So there isn't just names. Path comes first, pattern second, all files is third, and then full names is fourth. Okay. Most of the time, the first argument is the most useful one. That's the one you're most likely to change. Okay, so I really say this because, often it's very useful just to use the names, right? So here, if I list, I can just do full names equals true. It's going to take the default arguments for everything else, and it's going to update the argument for full names to be true, and it will give me the full name. That is probably the way to specify arguments in these. The only other way to do it is to write out every other argument up to the one you want to change. And then that looks kind of ugly. So use the names like full names equals true, question mark dir, and see what is inside these functions. I'm gonna show you all the functions we need as we go. I'm gonna talk you through. So the first thing we'll look at is variables. As with other programming and obviously graphical calculators, R makes use of variables. And this just means that we can store a value, a letter, a word, a table, whatever, as, a letter or a word. So we can store whatever result we have, a numeric, a table later on, an array. We can store this as a letter or word, and we can make use of this later on. It's very basics of programming. One thing which is a little different about R is when we want to assign something to a variable. And here I'm going to create a variable which is just a single letter X. It's the most common variable created in R, I think. I'm going to assign to it the value of 10. And we can do this two ways in R. You can either just do X equals 10, and it's going to give you X as the value of 10, or we can do this X assign 10. Okay, so R, I think, is one of the few languages which uses this assign. There is very little difference between assign and equals. This is a common question people ask me, why can't I just use equals? You can't use assign in function arguments. It won't let you. The real difference, well, two reasons. The reason assign is here is because keyboards used to have an assign button. and that disappeared. So now we're still stuck with a sign. The other thing is that as we will look later on at functions, it is possible to assign things to what I will say is the global environment. Okay, so you can assign things within a function, and we'll see this later on, and it only exists within the scope of that function while that function is running, and it disappears. There are some horrible tricks you can do where you can assign it to the global environment from inside a function, and that's really the power of this assignment. So I'll show you that later on. It's not relevant right now, but this is the most common question I get asked at this point. So here we're going to assign x to 10. Sorry, 10 to x. And now x will hold the value of 10. And I'm just going to do that in R one last time. I'm going to say that a lot, but then just keep on opening R. So if I do this, x is 10, right? Hopefully in our environment panel, I got other things, but I've got x is 10. Okay, if I press X, you can see it prints to the screen. So what was happening when I was just typing X 10 earlier on, it was creating that variable, it was printing it to screen, but it wasn't saving. Right? But here I can save it, and then later on, we can come back and actually use that. So variables, once we've created them, it's not like for those of you in Python where you have your concept of immutable, mutable objects. There is no such thing as an immutable object. We can change all variables in R at any point, which makes it both easy, but also unsafe at points. But here we're going to say we've assigned X to be 10. If I do enter on X, it'll show 10. If I want to, I can just replace that number with 20 now, and it's as if 10 never existed, right? The X is something totally different. We can also be used just as the values they contain, right? So here I'm going to create, or I have X as 20 now, right? I can treat it just like a number. Right? There is no assigning variables a particular class like you do in other languages like Python. I'm going to say this is an integer. Here I know this is a number, and I can add to it the square root of 25. And I'll get 25 as another variable. I haven't assigned it anywhere yet, but here I can do y. I can assign to the result x plus the square root of 25. And it's going to do 20 plus 5. And now y is 25. Right? So we can use variables with other variables or to create new variables. One of the most basic variables in pretty much any programming language is a vector, which would be equivalent to an array or something in most other languages. And a vector is, importantly, an ordered collection of values. And actually, it's an ordered collection of values of the same class. Okay, so the order is important. If I assign them, the first in the array is always the first in the array. Okay, if I want to reset it, that's okay. But it's important it has order. And important also is that it all is the same value, so same type or class. And that's as simple as I can't mix numbers with strings, right? So if I wanted to add my name to an array after 10 numbers, it's going to make all those numbers strings. Okay. So right now it's just a length 1 vector, right? I've only assigned one value to it, 20. And if I do length of this, it's going to tell me length is 1. Okay? Because it's a vector of length 1. There's only one value there. If I want to create bigger vectors, and obviously you're not going to be typing in your vectors most of the time, you're going to be reading them from files and objects, but sometimes you will. So we have to use this function C parentheses, and that's the combine function. And like other arguments, it takes its name, which is C, we get the parentheses, and then separated by arguments, separated by commas are our arguments. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right, and I get back a vector now, length 10, containing my results. Very, very simple. Length is another function. It takes here just one argument, a vector we want to get the length of, and it's going to give me 10. If, and then you're going to start to need some shorthand here. Typing out 10 numbers, 100 numbers is a pain, right? So there are nice, clever ways of doing that. If I want to create a stretch, of values, I'm going to do something like this. I will use a colon. I think this is similar in Python as I remember. So we'll do 6 colon 10, and it's going to give me a vector of numbers from 6 to 10, okay, which is going to save me having to do C and type them all in. If we want to create a stretch of numbers in R, actually the recommended way of doing it is using this function, seek. And we just give it 3 arguments here, and I've named them, right? And they're separated by commas. And I want to use seek to create numbers from 1 to 5 in steps of 2. I'm going to say by 2. And then it's going to give me a vector back, 1, 3, 5. Another thing we want to do a lot, we're probably going to use this a lot, is to do repeated stretches of numbers. So here we're going to do rep, and I'm actually going to give it another function result. I guess this is a vector, 1, 5, 10, and I'm going to ask it to repeat that vector 3 times. So that's going to give me 1, 5, 10, 1, 5, 10, 1, 5, 10. So that's a vector of length 9. I haven't saved it to anything, but that's another way of creating these stretches of numbers. So as we're going to see, creating stretches of numbers can be useful occasionally for things like indexing, which I think we're going to look at in the next slides. Okay. Again, if you want to learn more about these question mark seek, question mark rep, I'm going to say this a lot, but like question mark, the name of the function, will get you a lot of information before you start Googling. It's the place where it's going. Okay. So if we want to retrieve numbers, particular numbers out of these vectors, we want to get the first, the third, the fifth. We can use a different set of brackets. We'll use square brackets to identify the position within the vector, the index, right? The actual position, I guess there's no other better word than index. The index of the array we want to retrieve. Okay. For those coming from other languages, apart from R isn't zero-based indexing. Right, sad face. So usually in other languages, the first position in an array is 0. In R, it's 1, which actually makes more sense if you're coming from outside. You've never done a programming language before, but because it's different from every other programming language, it can annoy people like Python. But in this case, if I want to pull out the first value from my newly created vector Z, so here I've created 220 by 2, so 2, 4, 6, 8, 10, whatever. If I want to get out the first value, I just do Z, square brackets 1, and it will retrieve the first value. If I want to get the 8th value, Z 8, and I can get the 8th value. That is the 8th value, I think. We can also use this to get like multiple values out at the same time. So here we might want to get the 1st and the 6th. So I'm going to create a vector here using this combine function, which is going to create 1 and 6 for me. And I can use that then to index Z to get the 1st and the 6th number, which will be 2 and 12. And here we have it as a new vector. So hopefully, that we've had to type it in here, but if you had a really long vector and you need a stretch of numbers, using these things can be very useful to kind of create other indexes. Similar to other languages, if I want to get everything apart from a number, I can do minus. So I want everything apart from the 5th index. I will do Z minus 5, and now that's omitted from my particular function, my particular vector. We can also use, as I said, these things can be replaced, right? Any value within most functions, most data types can be replaced in R. I think all data types, nothing's protected. So here I have my stretch of numbers for Z. If I want to replace the 5th number with something new, here I just do Z5 and I assign to that, like I did when I created things. I use my assign function and I give it the number 1000, and now my vector goes 2, 4, 6, 8, 1000, 12, 14, 16, 18. Okay. So I can replace anything within my array, and I can replace multiple numbers in my array at the same time. We can also use, usefully, other vectors to index another vector. So in this case, if I create a vector containing 6, 7, 8, 9, 10, I can use that then to index Z, and I can say, give me the 6th, 7th, 8th, 9th, and 10th values of Z. And here I'm going to replace them with 0. And now we can see we've altered our vector so that these values now are 0. We'd already changed this one. So we can interact with these vectors through indexes, and we can replace positions or pull them out to create new vectors. So just remember, so far we've come across 2 types of brackets. We'll come across another one later on. But we have square brackets, which we use for indexing, such as this to get the first value, and parentheses we're going to use for function arguments. Okay. So vectors in R can be used for arithmetic operations, numeric vectors in R, as seen with other variables earlier. So, I could add 2 numbers together very simply. So here we can do standard arithmetic operations on whole vectors at a time. So I'm going to create a vector x, which is 1 to 10. If I then want to, make sure I'm charging. If I then want to multiply every single value in that vector by 2, I can just do x times 2, and it will times every value in there, will double them all. Right? So now I have a new vector called y, which is 2 times that. We can also use our vectors to actually kind of work together to produce arithmetic operations. So in this case, I'm going to add x to y. Okay. So then what it's going to do is add all pairwise values across this together. So if we look x plus y, the result is 3 here. It's because it's added the first value in x to the first value in y, second value in x and value in y, and it kind of worked along. Okay, so it's already doing something kind of clever for us. It's adding these all up in a pairwise manner. And it's saving me having to do anything clever, like in Python, I might have to loop through and add them together. Here, it just does it as a vector operation. Gets a little bit more complex when we start to add numbers together or vectors together which aren't the same length. Okay, so R, in the most part, will try and do something sensible, and if it can't, it will warn you. So warnings in R aren't necessarily an error. They're not a problem. Like, it still worked, but it's saying the result is not necessarily what you expect it to be. So don't ignore them. Because they don't break your scripts and you actually continue, a lot of the time, you just kind of go fuzzy and just don't look at it and carry on. Right? In some cases, it's actually telling you there's a problem. So in this case, we've got x, 1 to 10, and we're going to try and add another vector of it, just 1 to 2. And you can see it kind of recycles the shorter vector. So it's going to do 1 plus 1, 2 plus 2, and then it will do 3 plus 1, and then 4 plus 2, and then 5 plus 1, and 6 plus 2, 7 plus 1. So it's recycling this as it moves along pairwise, adding this together. The issue then becomes, what happens if I add 3 numbers, right? I got 10 numbers here. It's not going to fit in. It's not going to cycle to a regular number. And it actually tells me that longer object length is not a multiple of the shorter object length. So it's warning me that maybe I'm going to get an unexpected, or maybe that's not something I intended to do, but it still did it for me. 2 plus 1, 4 plus 2. Did it do it for me? 4 plus, oh, sorry, I'm looking at the wrong thing. 3 plus 3, etc., etc., etc. But take warnings seriously. Don't just ignore them. So we've looked at like numeric vectors. Hopefully they act roughly like we might expect. We can also create character vectors. Okay, we can't create mixes of the two. We can't create a numeric and a character vector in the same thing. And that's because it doesn't want you to get into situations where you're going to try and add numbers and strings together. Okay? So if we want to, we can create a string of, or a vector of strings, I'm going to call them. And here I'm going to, these are old buildings in London somewhere. I should update this to New York buildings. ICTEM, Commonwealth, and Wolfson. So we create a vector, and I can use that just like I did numeric vectors. If I want to look at the second value, I can do y2. And it's going to pull out the second value from here, Commonwealth. Great. We can also really usefully with character vectors, we can actually use these to assign names to other vectors. Okay? So here I'm going to create a vector 1 to 3, a numeric vector, in a really weird way where I'm both combining and also doing a shortcut. I'm not sure why I did that. So that's going to create 1 to 3, and then I want to assign some names to it. I'm going to assign the same length here, character string, ictem, Commonwealth Wolfson. And now I have the same vector, but it's kind of displayed differently to me, right? I can see that each of them have some type of name above them. Ictem, Commonwealth, and Wolfson. The really useful thing about this is then I can use those names as indexes, right? So I don't need to know what positions at that point. If I want to pull out the value for Ictem and Wolfson, I can use X, I can do my standard square brackets, and then I just provide an index here, but not a vector of numbers, a vector of strings. And it's going to match them up to these here, and then just pull out the two values I want with the name still there. If I try and provide an index which isn't in my vector, it's actually probably not going to give me a warning or an error. It's going to give me back a special value. So I'm looking for Strand. Yes, that's a London street. And it's going to give me a special value called NA. Anyone know what NA stands for? What was that? Did someone say the answer, or did I just imagine? Not available. That's the second one in my head would have been non-applicable, but not available. So we don't have an answer for that. Oh, here's the next bloody slide. Sorry. So, like in many languages, when there's a missing value, when a variable is missing, the value is assigned an NA value. And that's because we don't want just an error. We want to have a special value, which maybe we can capture and we can use or ignore later on. So like if we take the mean of a big vector and it has NAs in it, it's going to tell you an error. It's going to say, not all this is numbers. But there's an option, there's an argument to say ignore NAs. Right? So it will alert us, it will put it in there, but it will then allow us to kind of deal with them in special ways. So not available, not applicable, it's exactly the same meaning. Or not a number is another thing we're going to come across. And both of these need to be dealt in functions with these special arguments, okay? So it's going to allow us to handle these slightly different. A really useful function we're going to use with the vectors a lot is unique. So often you will have, and we're going to see data tables and something, but when you pull the information out of a, say a table, whatever, you might want to know what are just the unique values in that column. I just want to know every potential value I have in that column. One way to do that is to take a vector here. So here I've got gene 1, 2, 3, 4, 5, 1, and 3 again. If I just want to know the unique values in that, I can just use this unique function, and it's going to give them back to me. I think it gives them back to me in the order they appeared in that vector. Okay, so gene 1, gene 2, gene 3, gene 4. Another class of vectors we can deal with is logical vectors. So we've had numeric, we've had string vectors, I guess, and now we have logical vectors. So logical vectors in R can be two. You can define a logical in R two ways. If you type in true to R, that's a special value. Okay, I think that's true. Let me check. I think it gets highlighted in a special one. So it's a special value. It's not a string, right? If I typed in Tom, it's going to tell me that's not an object, right? But true it recognizes, and false it recognizes. Okay, and these are logicals saying something is true, something is false. Okay, there are shorthands to use for this, and that's T and F, but I wouldn't use them, and that's because things like there are situations. I mean, you'll get told off if you start programming and writing packages. They say don't use T, don't use F. The reason is, strangely, that you can't assign anything, or maybe this has changed now, but you can't assign anything to true. It's protected. So if you try and do true is 1, it's going to tell you off. You can assign things to T and F, I believe. So that's not as protective, but you can, in shorthand, if you want to, you can use that to create logical vectors, just the same way that we create other vectors. Okay. So logical vectors can be used then to index other vectors in a slightly different way. Okay, whereas before we provide the number, the position that we want to pull out. In this case, I have a vector the same length as X. I have true, false, true, false, true, false, true, false, true, false. If I use this as an index on X, and I give it Z, it's going to give me just the values back which are true. Okay. Right, so in this case, just those values which are actually true. A common task in R then is to subset one vector by the values. We have this really nice little operator called in, which allows us to match in the context of, say, A in B. And it's going to create a logical vector of whether the values in A match any of the values in B. Okay, so I'm going to create two lists here, gene 1, gene 2, gene 3, gene 4, gene 5, 1, 2, and 3. And then I have a second one, which is just gene 5 and gene 3. If I really want to say, just give me the values from here, which match any values in here, I can do gene list in second gene list. And it gives me back a logical index now where I have false, false, because 1 and 2 aren't at all in this vector. True, because gene 3 isn't that vector. False again, because gene 4 isn't, but gene 5 is. False again, gene 1, but then true, because gene 3 isn't that second. So this logical vector then, I could use to subset my original gene list and just give me back the values here, which occurred in my second gene list. Okay, so we're almost an hour in. I'm going to give us a little break in a few minutes. Here we go. The really lovely thing about logical vectors, where they really become useful, is when you start to use them with this. Yeah, please. Oh, great. So that's actually just exactly what it does. So you use, so if I look here, this should be 1 to 10, and Z is true, false, true, false. It will only extract values where true, where it's actually true. When it says false, it's not going to give me that value back. When it gives true again, so that's why we ended up with 1, 3, 5, 7, and 9, because the first value was true, the second was false, the third value was true. Does that make sense? It ignores the false, exactly. And that becomes really useful when we start to have logicals, logical operators like here. So in this case, just as an example, we have X is 1 to 10. If I then want to evaluate X and say, give me all the values above 5, we can say that the first 1, 2, 3, 4, 5 are all false, and then it's all true. If I use that now as an index, it will pull out just those which were above 5. So that's the real use of, it's not the best example, this first slide, but here we have a nice example. So we have all the common operators, obviously, in R. We have equals, equals, right? Is this number the same as that? So I would do is X equals 5. It will just pull out the first value. We have greater than, less than. We have greater than or equal, less than or equal. So we can use all these to create our true falses, which typically you're going to use to index, to subset vectors. Right now, a very simple vector, but later on we'll use them to subset rows, to subset columns. We may want to have slightly more complex operations. We may want to say it has to be greater than this, but also less than that, a range or something. So logical vectors can also be used in combination with these kind of operators here. And the operators, I think the most common are and, pipe, which is or reverse the operation. So it's like not. So in this case, we can say X is 1 to 10. Give me all the values greater than 4. But by putting this not in front of it, exclamation mark, is going to give me all the values which are greater than 4. It's going to reverse the logical, but are not greater than 4. So true, 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 and then all false. Very usefully, we can actually combine modern operators together. So we can say, give me all the values greater than 4 and less than 7. So it's only going to be 5 and 6. And then we can also do or, which is totally useless here. All the values greater than 4 or less than 7. Everything's true. Okay. So this can then allow, obviously, for much more complex kind of subsetting of your values. So in this case, if I've got my 1 to 10, and I want to pull out those which are greater than 4 and less than 7, I'll get 5 and 6. If I get my x and I want to pull out those which are greater than 4 and not less than 7, I'm going to get 7, 8, 9, and 10. Okay. We're going to use these a lot and practice a lot with these. So with that, we have our first exercise. So I'm going to take a little break for 15 minutes just now. We will continue with the rest of the session, so we'll do another hour, and then we'll close off for today and come back on Monday. So take 15 minutes now. If you need to head off to lab meetings, or if you need to go off, feel free to leave or come back. I'm going to leave you just for 10 minutes. Maybe if you have any issues, if you don't have R installed, maybe you could ask now. I think Alan can maybe help for this particular part. If you have any questions, let us know. Just give me a 10-minute break while I rest my voice. And I'll be back. Yeah. What's up, sir? Yeah, I absolutely appreciate it. Second year. Wow.
It's like an intro. Like that, yeah. I think for this whole class, I think what. Yeah. Yeah. Squat.
No one else ever came on. He was so happy. Eventually. When they kicked him out, he got the smallest pup. So I'm going to get started now in just a minute or so. And we're going to run through to lists today. So we got a few slides, but we'll leave us something for Monday. to check my schedule. Is there a Rose in this class? Okay. She said she was going to come. Maybe she's the one who left. So do you mind if I do that at the end? I'll come back, but absolutely I will. Yeah. I think we have, at some point we do a reproducible R session. We go into a bit more detail there, I believe. But absolutely I will. It was fascinating. I lost my charger for a year. And here it is. I left it in here. I know. That is great, isn't it? Yeah, it's definitely mine. It's definitely mine. All right, now I'm having to hide all this stuff. So these extension leads, they were warning me don't leave them in here because someone will steal them. Probably me. I need more extension leads. These were a commodity though, these chargers. They seem to permanently be somewhere without a charger. In a lot of our YouTube videos, there's a bit where I go, shit, I'm running out of battery, and then suddenly it just goes black. Okay, so we've dealt really with the most basic type of data, which is vectors. Most times, most data we're going to look at comes within some type of format or multiple. Like Excel, which you probably use, or OpenOffice, or LibreOffice, or whatever we're using. I think this is OpenOffice. We have a concept of a table like this. We have names for the rows. This can be a gene, whatever. Columns, these are usually samples. And this has some way a named index. The rows have a named index and have values. So, if this was sample 2, 1, it's called. So a lot of data which we will deal with will be some format of a table. And we have a few different ways of handling tables in R and other languages as well. The first is common across everything, which is a matrix. Okay, so matrix is just a 2D. So we can create matrices now using not the C function, but the matrix function. And we need to supply it with some data. So here we can actually supply it with a vector. And it's just 1 to 10. Okay. And we can tell it, I have 5 rows and I have this many columns, 2 columns. And then it will populate, it will create a matrix for me here, 5 by 2, so 5 by 2. And by default, it's going to populate it first by column. Right. So it does the first column, it puts the first 5 numbers, and then the second column puts the next column. By default, we can change this. We can also create a wide matrix exactly the same way. Here I'm just going to put 2 rows, 5 columns, but it does the same thing. Sorry, it's a little bit off the end of the screen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is going to create a matrix for us. Right now, it's got our indexes here. So this is the first column. This is the second column. This is the first row, second row, third row, fourth row, fifth row. You'll notice we have now commas in our indexes. We'll talk about that in a second. But first, second, 1, 2, 3, 5. We can, and often this is one of the things I do change a lot. We can control how we fill this. Okay. So in this first case, we were doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If I want to go the other way, right, I want to fill by rows first. Sometimes we're kind of turning one object to another. We might want to do that. I just have to add another argument. So we have our vector, our number of rows, all separated by comma, like all arguments are. And here we have by row. By default, that will be false. I'm now going to set it to be true. And now 1 to 5 is there and 6 to 10 is there. Okay. We can we saw earlier on, I was using this function length on my vectors, and that was giving me the total length. So I have similar functions to look at the dimensions of my matrices. So here I can do dim, and it will give me a vector again back. That's 2, I have 5, 2. So I have 5 rows. Rows go first, columns go second. That's a common thing in R. 5 rows, 2 columns. If I want to get just the number of rows, I can do n row, number of rows, and n col, number of columns. Okay, which makes you think, why isn't length actually called n as a function, but it's just not. If we want to create then maybe stitch 2 vectors together, we can actually do this by using like an advanced version of C, with C bind, column bind. And this will attach 2 columns or 2 vectors together as a matrix. We can actually use this to also combine 2 matrices together, right? It's going to combine in a column-wise way. So here I'm going to take 1 to 5, and then I'll take 11 to 15. These should be the same length. If I then do C bind, X and Y, I get a new matrix. And you can see we have 1 to 5, and then 11 to 15. Okay. In that order that I've said. X went first, Y went second. That order controls how they're put into the matrix. You can also do R bind on this new matrix I've created, and this will be not column bind now, row bind. Right, I'm going to add Z, which was just 2 numbers, 21 and 22. Okay. And now I have them attached to the end of my matrix. So notice R also did something kind of clever for us. When I did C bind X and C bind Y, it actually, in comparison to these matrices I created here, where we have no name for a column, when I did it using C bind, it automatically assigned the name of the vector to the name of the column. It's kind of clever. So this column was X because it came from X. This column was Y. And then when I R bind the Z in, I don't have names for the other ones, but I got Z because that was what I was R binding. Just a neat little functionality in there. Again, like when we were doing arithmetic operations, when things don't quite match, when I try and add 2 vectors which aren't compatible, one's not multiplication of the other. Here, if I try and put together matrices which just don't have the same number of rows or columns in an awkward way, it's going to give me another warning. Okay. So in this case, I'm going to do create a matrix. I'm going to try and put 5 numbers, 1 to 5, into something with 6 total values, but 2 columns and 3 rows. And again, it's going to give me a very sensible warning. Data length 5 is not a submultiple or a multiple of the number of rows. Okay, and what happens is I get recycling here. I get 1, 2, 3, 4, 5, and 1. Okay, so it's tried to fill my matrix in a sensible way, and it's just ended up recycling the last value. R tries hard for you, right? Not necessarily what you want it to do, but it's trying. Same way, if we do R bind, but in this case, the longer value is clipped. Okay, so here I'm going to try and R bind a 1 to 5 onto my matrix, right, which is way more columns, or would need way more columns than I actually have. It's not going to try and fill in additional columns for me. It's going to say, number of columns, the result is not a multiple of whatever, and it's just going to add the first 2 values. Okay, so here I just got 1 to 2 on the bottom of the matrix, and I actually threw away the rest rather than trying to extend it. Okay, but it should be a warning, and it's told me the problem. We saw that R did this by default when we did cbind or whatever, but we can assign column and row matrices, and these are very useful, as we will see later on. We saw for vectors for indexing. So here, if I create a matrix which is 1 to 10, I haven't done by row, so it's gone 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can then assign some numbers, some names to these columns by using not names now, but col names and row names. Okay, so we use names to assign to a vector. Here we're using col names to assign to the column and row names to assign to the rows. To do this, I'm going to use another function, which is really useful, called paste, question mark paste, if you want to learn a bit more about this. But what this is going to do, it's going to take the numbers 1 to 5, it's going to paste to them a column, and it's going to put a separator between this and every value of this of an underscore. Okay. So this is my separator value. I could set that to anything. It could be a star, a space, another letter. But it's going to create a vector of length 5, column 1, column 2, column 3, column 4, column 5. And I then use that to assign that onto my column names and my row names. So now I have my named matrix, which looks a little different from the matrices we were kind of creating earlier on, which had the actually explicitly wrote out the index.
Let's say I could just say like create a string named like all 1, 2, 4, 6, 8, probably the 5 or something. Is there a way to like keep that like
So explain that to me again, sorry.
like I guess it looks like the paste function takes like a 1 to 5, treats it like a vector, creating call 1, call 2, call 3, call 4, call 5. Let's say that
Oh, I see. That's interesting.
that's something I
Yes, yeah, maybe. Actually, no, I think I get what you mean, actually. Now. I wonder if so you want column 1, 2, 3, 4, 5.
yeah, like all concatenated.
Yeah, no, I see what you mean. Maybe you would do it like this, actually. You see. Actually got me thinking. Collapse, would that work here? So I wasn't sure how I would get that to work here, but we can have a look. Yeah. Oh, you can also just do collapse like what you want to collapse, right? So I usually use that for kind of combining vectors together. But yeah, here we go. I guess that hasn't quite done what you want, right? Because you're getting now column, 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 column.
That kind of works though.
I think you can do
Yeah,
multiple.
I think that's kind of what
I think you could do multiple pastes as well. You could do a paste within a paste and get this. Maybe. I don't know why we'd want to do this, but
yeah.
I think that might do like that.
Yeah.
Okay. Yeah. There probably is a shortcut as well. But, you know, that's what I would do. Geez, making me think. Right. So then we can also obviously column names are like names we can both assign and we can get. Here I'm assigning. If I want to get the names of a matrix, I can do col names. It will tell me the names. I can get row names too. So indexing, we can also index matrices, two-dimensional things in a very similar way, so that we did to vectors. The only thing is we need to now take into account, are we indexing by the row or are we indexing by the column, or maybe we're doing both at the same time. In R, when we want to index by row, we're going to put the row first and then we'll do a comma. If we want to index by column, we'll do a comma first and then we'll do column. Okay. So we can actually see this in action, which is probably the best way of doing it. So here I've got my narrow matrix. And you can see here, we've got, we want to pull out the second row first column. We can do 2, 1, second row first column, we'll bring out that as a vector. If I want to pull out the entire second column, I just don't specify an index for before the comma. So I don't specify what rows I want. Okay, so here I can just do 2, and it's going to bring out that second column. Similarly for rows, if I want the third row, I just specify 3, and it's going to give me those values from that third row. We can, of course, start to combine this just like we did with indexing, just like we did with logicals earlier on. We can use that to index our columns and our rows. And here, if I want the second and third, just do C2, 3. I'm not sure if we're going to do this perhaps in the exercises, but obviously you can then use this with logicals as well. If we've assigned column and row names, we can also use these column and row names to index. So here I'm going to assign my column and our row names again. And if I want to pull out the first column, I can just use the name of the column. And it's going to bring me, because I've named it now, a named vector back with the names from the rows, 1, 2, 3, 4, 5. If I want to pull out just row 1, I can use the name I've just assigned to the row, and I will pull out 1 and 6. If I want to do both, I can obviously do the same thing. Just as I use with a number index, I can specify the column and row names. So vectors and matrices can also be subset by, I'm going to do logical vectors. Okay. Right, so again, like we were doing earlier on, we can use logical vectors now, but perhaps this is more useful for things like columns or for tables. So here I'm going to use that first column. So I'm going to just show it here, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And what I'll do now is just take that first column, and I'm going to get which ones were less than 5. If we look, they're all less than 5 up until this last one. So I'm going to get true, 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 false. And then I can use that to subset my matrix just to give me the rows where that first column was less than 5. And now we can see I got 1, 2, 3, 4, and that last column, last row, sorry, is no longer available, right? Subset using these indexes to remove that last row. A really powerful feature of R, we can do some type of arithmetic operation, and we're not going to go much into this matrix multiplication. I'm just going to show you some simple things here. But now we have a numeric matrix. This is going to come up again now, the fact it's a numeric matrix. If I try and add 2 to a particular value here, I can say narrow matrix, first row, first column, add 2. It's obviously going to give me 3. But I can also add, like we did with kind of vector multiplication or vector additions and operations earlier on. Narrow matrix, I'll take the first row and I'll add 2 to both those values. So 3 and 8. What's very cool is we can actually apply this to whole matrices, and most functions like sum, min, multiplications and stuff, you would apply to the whole matrix in one go. So here, if I want to get the mean of my entire matrix, I can just do mean, and it will treat it as if it was just one long vector. And I'll get, should be 5.5. Okay. As with vectors, we can also replace position. So here I want to replace the first row, the first column. I can replace that with 10. If I want to replace an entire row or an entire column, I can just provide the index, and here I can assign 1. So I don't need to explicitly write out every like 1 5 times here or whatever. I can just say 1, and it's going to fill that entire column. It's going to recycle the value 1 across all my values. So this is a really important thing to know about matrices, is that they can only contain one data type, just like vectors. Okay, so as soon as you, I'm not going to say pollute, as soon as you add one string to your matrix, the whole thing can't be treated as a numbers entry. So in this case, I'm just going to replace the first column, first row with something not a number. I could have done something else maybe, but not a number. And you can see, you know, before it was 1, it was written out differently. They're numeric. Now, even though I'm not touching the second column or any of the other rows, the whole thing becomes string. Okay. That is important really in base kind of R, because the reason matrices are kind of fast is because it assumes that it's all one data type. Okay, so as soon as you start changing any of the matrix, you're going to become a string. Now you can't mix logicals with numerics, you can't mix numerics with strings, you can't mix any data types. So now, even though I haven't done anything to the second column, if I start to do any type of multiplication on it, it's going to say not numeric, non-numeric argument to a binary operator. And now we actually see an error. Okay? And errors are just they're going to stop. They're not going to give you a result. So we have some exercises. I'm going to go through that. to assign it. So that's like a big difference in R is we don't have, when we're talking about pointers and stuff, like in some languages you change it and it's changed even though you haven't explicitly assigned it. In R, you have to assign it. It's totally gone if you don't do it. So a special case of a vector is something called a factor. Okay? So a factor is used to store data which really could be grouped as categories. So categorical data. Specifying data as categorical allows R to handle it in special ways. Right? So I think we'll see this later on, but like functions you would then normally apply to a like summary is a function we can apply to a vector and it will give me the quantiles of it. When you start applying it to a factor, it handles it differently. So factors are a different class and they have some slightly different rules. So we can create a factor from a string vector by first creating the string here. See, I'm going to do male, female, female, female. And we have vector example. And then I'm just going to turn that into a factor by using the factor argument and supplying this vector. Okay. And then we have our vector back. And we have, it looks a little different, right? It's not quoted anymore. It's male, female, female, female. And we have this concept of levels. Female, male. Notice the order. Right? Female, then male. We can actually retrieve these levels directly from our factor by doing levels on that, and it will give us back a vector now, a normal vector containing the levels inside this factor we created. So these levels are effectively every different value which could occur in that factor when we created it. Right? So we know, and that's one of the advantages of factors, we know all the potential values here. Right? They're only going to be female and male in this factor. It's one way, yeah, it's kind of like that, except, you know, this is inherently built into factors, and we're going to see some issues. It's both an advantage, but also you need to handle factors differently. This is all the unique values in there. But it's, you know, they are unique because that's what it's trying to explain. It's trying to tell you all the unique values. But yeah, one way of getting unique values, I don't think it would be as fast as to create a factor and then extract the levels if you wanted to. I imagine unique is way faster. And working with factors is slower than working with vectors. Right? You're not going to notice this most of the time. If you start doing big data, just because you're creating an object which has different rules, has some structure to it. Okay, so an example here of the difference of applying a summary to a vector of the same information. So vector example, male, female, female, female. If I apply summary to that, it gives me something useful. It tells me the length. It tells me the class, character, it's the mode is character. If I do that on factor, it actually gives me some really useful information. It tells me how much of each of these categories there are. I have 3 females and 1 male. So there's, you know, the same function applied to different classes can give me a slightly different result. Okay, and that's because under the hood, R is doing a little bit of work for you. So in our factor, you know, and this wasn't any statement, the levels came out obviously female and male when we first looked. Does anyone have an idea why they came out as female and male? The order here. It's simple, it's alphabetical. Right? So it's very lazy, it just looks at the alphabetical. It goes through this, even though male was the first entrance, it wasn't like working from left to right. Alphabetically, female came first and male. Okay, we can control this, and when we create the factor, setting the levels. Okay, and in this case, we're going to set male to be first and female to be second. And now we're going to have male, female here in different order. And we're going to have, when we do the summary, it's going to come off in that order as well. The big reason for controlling levels is later on, we're going to start doing plotting with things like ggplot2. And it's levels which control the order that they appear in the plot. When we start to do DSeq, differential expression analysis for RNA-seq, it's levels, the order of the levels which control what's your baseline. Okay, so we need to be able to control these and affect these. And I think especially ggplot2 This is how we control the order. A slight pain. Oh no, this isn't the pain bit. This is reasonably pain. We'll get to the pain bit. So we have kind of multiple types of factors, right? We have the idea of ordinal and nominal. So in these levels, there is no natural order. This isn't, again, a statement, male and females are equal, right? But there isn't actually an order of what is greater. So if I try to do something like my first is less than my second, so here I'm saying male is less than female, it's a controversial set of descriptions, right? It's just going to say, what are you talking about? You know, warning and ops factor, this is not meaningful factors. Okay. But actually categorical data can be meaningful. It can have order, right? So we can have ordinal factors where we do have order. And in this case, I'm going to create factors. Maybe I bin my results into small, big, large, or whatever. Here I've just got small and big. I'm going to set my levels. Okay. I'm going to say order equals true. And now when I just look at this, you can see the levels are displayed differently. Previously, they were just like next to each other. Here, we now have small is less than big. Okay. And if I do factor example 1 is less than that, if I say is small less than big, it's going to tell me true. Okay, so that you can add order to your categories as well. That can be useful again for plotting later on. Yeah, here we go for the pain. So when we set these factors, right, if I don't set my levels, it's going to give me that default order of levels. So here, alphabetically, I'm going to create a vector small, big, big, small. I'm going to create a factor. And if I was to look at it, the levels would be big, then small. I haven't put any order there, so it's just done it alphabetically. I can change my factors like a normal vector here. If I want to change the first value now to be big, we can see here, big, 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 small. I've successfully changed it. If, though, I try and create or assign to that first value something which isn't already in my factor, so in this case, I've only got small, big, small. It's not in my levels. If I now try and add huge, it's going to say invalid factor level because it doesn't have that available to me here. It's not a category within my factor when I created it. So I can't add new values there. And that's something which I think a lot of people get upset about. We'll see why in a few slides. So in this case, when I do it, it's going to let me, it's going to say, warning, invalid factor level. Because this doesn't exist in my levels here, it's just going to assign it to BN. And then it's going to be a future problem for future us to solve. What we can do, though, is at that point actually update the levels within our factor. So we can use this levels function not just to extract the levels, right? We can actually assign them. So here I'm going to reassign them, and I'm going to say big, small, and I'll add huge. Now, if I add huge to that first value, great, I can now use that as it is. Okay. So any values within this factor need to be within the levels. Naturally, when you create factors, if you create them like this, it's going to have all the levels, right? It's when you start to update it with new values which weren't there originally, it's going to give you that. This actually became a problem in data frames. We're going to see that in this next slide, why it becomes a bit of a problem. So data frames are, and anyone doing Python, pandas, right? Data frames are fantastic, really are, because they're matrices which aren't limited by having one type of data type. You can store lots of different data types across these columns. I think it's across columns, not rows. And this is really what we want to do. Most of the time, we're going to have some annotation in our first few columns, and then maybe we have numeric that we actually want to do some operations on. Right, so we have this special thing in R called a data frame, which is now being expanded to other languages. And just like factors, there are kind of special things we can do with data frames. When you read data into R, by default, most of them, I think by default, you're going to get a data frame. You're not going to get a matrix. Okay? So that's worth noting that you might need to convert it to a matrix for particular things. So creating a data frame is super easy. We can just use the function data.frame. And what we're going to do here is just have some different types of data. 1 to 4. Well, then that's going to be a string, a vector string. Then we're going to create a factor. We're going to repeat male and female twice. A factor. And then we give some numbers. And then I'm going to create my data frame. I'm sorry, this has gone a little bit off the side. By doing things like name. So I'm going to have a column called name. I'm going to put my patient name in there. I'm going to say I want a column called type. And I'm going to put my patient type there. And then I'm going to have survival time. And I'm going to assign into that the survival time. So from these 3 different types of objects, 2 the same, maybe 1 factor, but string, numeric, factor, I can then create my data frame, which looks kind of normal. There's no quotes or anything here, like with matrices, right? And then I can operate on this. Okay. These can be indexed just like matrices. Okay, so under the hood, it really doesn't matter at this point. I can just take survival time and say I want something greater than 10. If this was a matrix, this would say this is a numeric. And subset down to my rows where the survival time was above a certain number. Oh yeah, unlike matrices, actually we have a really nice kind of functionality using this dollar symbol, I guess, right? So if I want to extract the survival time column, I don't need to index it with square brackets, comma, the name of the column or second. I can just do dollar survival time, and then it's going to give me that out. Okay. And then I can actually use that to make my indexing look a little prettier. I often find this looks kind of ugly. Here I can do the same thing as previously, but I don't need to set the column. I just do dollar survival time less than 10. A nice little feature of this is that you don't need to type in the whole name of the column. So here I have name, type, and survival time. I can do dollar serve, or actually in this case, probably dollar $s, right? And just pull out that column. Right? That won't work if I do it like here. Right? But for data frames, it does. As long as this can recognize the column. So if I had 2 columns which started with S, I can't use S just to index it. But in this case, it's going to do some type of work with autocomplete. So already you can start to see why data frames are a little bit slower, because it does stuff like this. It's giving you a bit more functionality, but at the cost of speed. You're not going to notice this for the data you're looking at, but when you start, you may do, I don't know what you're looking at. But once you start to get millions of rows and lots of columns, it starts to make a difference. Nope. Yeah, it looks like that, and it knows, you know, this can only match this column. So it's kind of clever. We can also, and I find this really useful, on the fly, use these dollar things to make new columns. And this just seems much more natural to me. So if we do dollar new column, I can do rep and I can add whatever I want here. I'm going to rep new data for the number of times for n row my thing. So for the number of rows I have, I'm going to repeat new data. I'm going to assign that to a column called new column, and I get new column. Okay, it's just a little bit easier than working with matrices. I can also do replacement in much the same way, right? And this is going to be the sting. So here I want to take just the rows where survival time is less than 10. And then in the survival time column, now assign it to 0. Maybe I decide if you live less than 10, you might as well be 0. That sounds harsh. But for whatever reason I want to do that, I can use this kind of complex operation here, and I can just replace those values with 0. It's great, just like a matrix. I'm getting all the advantages. A slight problem starts to come again with the fact that we have a column there which is a factor. So even though we're in a data frame now, this column type is a factor. If I then try and replace with other, it's going to give me the same warning it gave me for a factor. And it's going to say invalid factor levels NA generated. So I'm trying to put into here, it's only got male, female. I'm not sure we explicitly looked, but I didn't add any other levels. So trying to add to it now other, it's going to say invalid level, and it's going to put an NA there. So we can now, I'm just looking ahead to see what if I make a complaint from this point. So it is possible then to update these data frames just as it is with standard factors. So if I have created a factor here and type, I can reassign levels just to that column. So this column is a factor. I can go levels and I can add in now my additional level, which is other, right? And now I can replace a value. So now I can have other. I'm not going to get any. Not sure this is really meaningful anymore. But if you happen to have R, which is over 3 years old, this was a big problem. Because what R, when you read data into R, it automatically turned any character columns into a factor for you, and then replacing them pretty hard. Some point around version R4, there was probably enough complaints to the R consortium to say, change this basic functionality, and it changed. So now when we read it in, it isn't a problem. We can explicitly say data frame, and when we give it these columns, we want data, patient name, patient type, survival time. We can explicitly say strings as factors. In this case, every column which is strings, whether it's a factor or a vector, it's going to force it into a factor. That may be useful for you. You may want to treat it as categorical data. But then it means that if you're going to try and start replacing things, here I'm going to add patient X. This wouldn't have been a problem when it was just a vector, but now it's a factor. It's going to give me this. We can fix that. Here I just set strings as factor equals false, and this is the default now. So this isn't really a problem for you, but maybe worth knowing a little bit for historical reasons. A useful function, and especially now we're going to start to look at tables and stuff, is order. Order effectively for numeric vectors, order by default returns the indices of a vector in that vector's increasing order. So let's actually see that. If I go test order here, 20, 10, 30. So we have 20, then 10, 30. I can control the order that it's going to give me back. And by default, it's going to do increasing. That's good for some values. Maybe for if I want to order by p-value, I want it to be increasing in that way. But I can also reverse it and go decreasing. If I'm using t-statistics or something and I want to go the other way. So let's give it this test order where we have 20, 10, and 30. We want it now, it's going to be increasing, or decreasing. Right? So the first one, if I was to do decreasing, would be the third. So it's saying the third should go first now. Then the second would be the next value. And then the first would be the next value. And then the second would be the last value. Right? So the third value in this test order thing is my highest value, decreasing equals true. Then 20 would be the next, and then 10 would be the third. Okay, so it's giving me the indexes I would want it in if I wanted to order it. I want the third first, the first, and the second. So I can actually just provide that to my vector. And because I'm providing the indexes it should be in, it's going to reorder it for me. Now it's 10, 20, 30. I can also change that. Oh yeah, sorry, this was with that. This is decreasing equals false. If I do decreasing equals true here, we change the order. Okay, so that's pretty nice. We can order this vector. This becomes particularly useful when we start to get onto things like data frames, right? When we want to order the whole table by a particular column. One thing to note then, and this will sting a fair few people, is you may have NA values, right? How do you order NA values? You don't know what they are. They're not. So here I'm going to deliberately put an NA in my vector in the third position. And when I run order, we actually have, like I was saying earlier on, like special ways of dealing with NA. We can say NA last equals true, or we can say NA last equals false. Okay. So in this case, if I say NA equals last equals true, it's going to put NA at the end. If I say NA equals last equals false, it'll put NA at the beginning. I'm not sure if I'm going to go into much detail, but this can be a problem when you order your table and it has NAs in it. your NAs that end up at the bottom of your table, right? Some people will take, I want the top hits, I want the first 3 rows, and I want the bottom hits, the end of my table. If you're putting all the NAs at the bottom of your table, it's just junk there. It's not actually in order. So you either remove the NAs and order it, or you need to be aware of that. And this is one way to kind of control that. So we can then use this trick to kind of order data frames. We have our data frame here, name, type, survival time. And it would make sense that I want to order this by survival time. Okay. So to do that, we know we can index data frames using either rows before the comma or columns after the comma. So I'm going to provide the indexes to the rows, and I'm going to say order by the survival time column, and I want it to be decreasing equals true. And now we have our data frame re-indexed and reordered such that 30, 20, 2. What's really useful is we can actually do this across multiple things. We're not just ordered by one. Maybe you want to first order by type, then you want to order by survival, so you can keep the here males or females together. So we just provide the ordering preference in kind of this order here, and then separate them by commas. So first I want to order by type, comma, then I want to order by survival, comma, and then I want it to be decreasing equals true. Okay, so first it's going to do male and female, and then it will do survival time. Okay. In this case, males. Geez, males don't survive very long. I never noticed that until I looked at this. Okay. Cool. So that's then ordering tables. Something which we're going to do a lot. Let's see what I got. Just 2 more slides. Something we're going to do a lot is we're going to have multiple tables. Maybe we read them in from multiple sources. You have your metadata on your information, and then you have your values, and you want to join these 2 tables together. I have a common column. Patients are in both my tables, and I want to bring this information into one table. So we can do that by this concept of merging. Okay, so here we're going to have data frame, name equals patient, patient type, survival time, and it looks like this. We're going to have a second data frame, and we have some values in common, right? So this contains height, this contains survival time and type, and we only have the first 3 here. We're not got the 4th patient. Okay. If I want to merge these 2 together, I can actually just use, and there are lots of different ways of merging data, but this is the base R. I can use the merge function, and I provide the 2 tables I want to merge by. I provide a by argument, and the by argument can actually be, I think I have this in an example, so in the exercises, but I'll say now anyway. It can either be the index of the column you want to merge by. So here it's going to be the first column, but you can actually also provide the name of the column you want to merge by. Right? And so you can say name here, and that can be useful if the first column isn't name in both. Maybe the name is in the 5th column of the second data frame, right? It's a lot easier that way. Here we're going to say all equals false. Okay, and that's important because what we're going to get back is only a data frame containing information where we had common patients here, common things to merge by. Right? So patient 4 got lost. Right, I have this information, but I had nothing in the second data frame. I didn't have a height. As we will see in the examples, if you want to, you can say all equals true, and you will maintain the patient information, but you just won't get values for height. You will get our NA back. We'll see that in our examples. Okay, so I'm going to stop here for today. I don't know what the time is. Oh, almost perfect. It's been 2 hours. I'm going to stop here today. I'm going to be around. We're going to, if you want, install R, look a little bit at GitHub. Alan's here as well. He's happy to help. I'd like to say that for other people. Very happy to help. So please hang around or head off. You know where the issues are. And you can also email us if you have any questions. Maybe, Alan, you're okay with me putting your email up, maybe, and I'll do that next time. Yeah, sure. Well, geez, you're going to get so much hassle. One thing before you go, and just because we're talking about it, there's a few things I haven't quite shown. So one thing I was making earlier on is R. So we're talking about R in terms of speed. So one thing I just wanted to point out is I was looking at the top most popular programming language. Python way at the top. Not Python. I wouldn't really consider R a programming language. R is a scripting language. If you're going to do big things, you're going to probably, if you're going to build software, often you're going to be doing this in Python. If you're going to be doing your analysis, you're probably going to be doing that. That's just the reality of my life. But there is this kind of idea that, it's not the one, is that really R is slower than most things. So, if we look here, this was an advert for Julia. I'm not sure if anyone knows this. It's another statistical language. Anyone ever looked at Julia? Yeah. It's very fast, but maybe not super popular. But just going from left to right, C is, universally one of the fastest languages. What lots of software is written in, and you can see R way over here. You can also see Python, kind of next to R, not at the top, but strangely, JavaScript did really well. JavaScript's what runs your web pages. It's super fast, apparently, because everyone uses it. I just want to remind people that, R isn't necessarily written all in R, right? So R under its hood is all C, or at least 43% of it's C, right? So again, we talked about functions and having to use functions. This is where the real speed comes in R. If you rely on functions to do the work for you, you'll find it's a lot faster. If you try and calculate means yourself, doing things like adding the numbers and dividing by the total, which you can do in C, you can do in Python, it's fast. It is way faster to find a function to do it for you. And that's, we're going to repeat that a lot. Well, coming from Java, where that's absolutely not the case, right? You write the functions yourself, it was a real struggle for me. So invest on finding the right functions. And I'm going to try and show you what you need for this class. But I assure you it's worth the Googling, it's worth looking around, because that's where the real speed comes for R, but also for Python. That's where a lot of the speed comes. So we just talked about data frames, and we're going to talk a little bit. My computer's giving up. So you can see here, maybe not here, but there are this concept of dplyr. Has anyone here used dplyr, tidyverse? Exactly. So this is like a different ways of using data frames. Okay, we're not going to cover it unless you particularly want me to cover it. We have notes on it. The reason I don't cover it, it's super popular. ggplot's probably more popular. It's not base R. So if you start to look at functions, and you look in the question mark help, you will never see a dplyr of help, only if you're working at tidyverse. So you need to know data frames. Talking about speed, dplyr is actually quite slow. Right? It's so easy to use, but it's so slow. When we really want to get into speed is this thing called data table. And we're not going to cover this at all, I think. We may do. But if you really are starting to work with big, unwieldy tables, and R's taking 30 minutes, an hour to process stuff, which it really can, data table is incredibly fast. It rivals anything you have in any other language. It's super fast, all written in C. So, if you do get stuck, you can reach out to me. I think Alan's nodding a lot, so I know he uses it then. If you come across, you already have tables which are just unwieldy now, let us know. We can either throw some notes together for the course, or we could just provide you with some information. Great, that's it for today. Thank you very much. I'm going to stop the recording. Stop share. Stop the recording, and I'm going to be